All right, hello everyone. Welcome back. We are going to wrap up Unit 4 today, which was all about line coding, mostly baseband coding, but we're going to try and push that into a little bit of channel coding today. And then we're going to start on the unit that I titled OFDM. But when I was looking at my lecture notes, I think I'd like to start in a slightly different place than just jumping straight into OFDM. And so the notes that I published yesterday, very little of which currently talk about orthogonal frequency division multiplexing. But I hope to add to those because I still want that unit to get to OFDM, but I think starting in a slightly different place might help it make sense in the long run. So before I jump back into the line coding lecture, are there any questions from your end? I did hear that the video that I posted of Monday's lecture had a Zoom window in the middle of the slides, which was not helpful, and I will do my best to avoid that today. Okay, so I want to call our attention back to this slide, in which we talked about the general pulse shaping idea of kind of maintaining total spectral density by shaving off the corner of the rectangle and pasting it down here. And then we can quantify how much we're shaving by this roll-off factor. The book calls it little r. Other sources are going to call it alpha or a. But the idea is that you shave off nothing, then you have kind of maximally dense power spectrum. But you pay for that with long tails in the time domain. And the more you shave from 0 to 1, the more your frequency domain spreads into adjacent bands. But you, in exchange for that, you get less kind of inter-symbol time-wise interference. So the eye diagram demo that I had at the end of last lecture was okay. I wasn't super pleased with it. So I'm gonna rather bring up a Simulink diagram that I think it does a better job of illustrating what I'm talking about. So this is pretty simple. This is all looking at the transmitter side. So we're not doing any kind of channel impairments at this point. But what we've got here is a random integer between 1 and 4. We're just going to do 1 bit per second. So you can think of these as like normalized seconds. And yeah, random seed, all that other good stuff. And so for every frame, we get 1 integer between 1 and 4 inclusive. That gets sent to this QPSK block, which takes those integers and maps them into QPSK symbols. And this is kind of cool. Like this block in Simulink gives us the ability to view the constellation diagram. And this says, okay, if a 0 integer comes in, it goes here, a 1, a 2, and then a 3. That's kind of interesting. Anyone care to comment why it goes 0, 1, 3, 2 instead of just 0, 1, 2, 3?
Well, I was assuming that they're using ones as negative in some sense and zeros as positive. And so you have both negative on as a 3. Like if it's a 2-bit, if it's like a 2-bit symbol,
Mm-hmm.
and you have 1 1 down here, that means that Q and I are both negative.
Okay.
And that's why they did it that way.
Interesting. Yeah, I like it. I think that, yeah, that actually gets at not just the convenience of it, but if you think about in terms of your probability of making an error, it's easier or it's more likely to make an error horizontally or vertically than it is to make an error both horizontally and vertically. So if the symbol in this quadrant differs in bits by 1 from this quadrant, then crossing over here, you're only going to make 1 bit error, even if you make 1 symbol error. So putting a double 0 here and a double 1 here makes the possibility of a 2-bit error, but a single symbol error, the least likely, if you think about it that way. So now any of the quote unquote easy to errors to make, i.e. crossing horizontal or vertical horizontal or vertical, result in only single bit errors, but the diagonal errors in both cases would result in double bit errors. And you don't get that if you put these in the kind of like counting orientation that I would by default make. And so that's actually what this constellation ordering is. The gray ordering is specifically so that symbol errors are more likely to lead to single bit errors than double bit errors. So a fun little tidbit there. In fact, if I change this to the other option and view the constellation, close, binary, apply, constellation. Yeah, so now it's 0, 1, 2, 3. So kind of like the just counting way. But that is technically more likely to lead to more bit errors than the gray coding. Okay, doesn't really matter for us. So let's carry on. And then this is a raised cosine filter. So this is why I showed you that slide, because we get to choose the roll-off factor for this filter. So what I want to do is I want to start with a 1 roll-off factor. So remember, this means that we are compromising the most in the frequency domain. So we're letting the power smooge out over more band, but we should see a very nice performance in the time domain. Okay, because this should make our sinks really nice and tight and die off really quickly. And the reason I'm doing that is because the eye diagram is at its heart a time domain measurement, right? It literally is time in the horizontal axis here. So let's go ahead and run that for 1,000 bits, or sorry, 1,000 bits. So this would be 500 symbols. Wait for it. There we go. Okay, so this is a 2 eyes worth of data. And we can see that these lines are fuzzier than they were on the analog discovery, and that's because of the cosine filter. It's because even with the highest roll-off, we're still going to get this jitter, and that comes from the fact that one symbol is still alive or has non-zero voltage when the next symbol starts. And we can see that depending on the order of the symbols, we are going to get, looks like 3 distinct kind of bands down here, but that we are seeing pretty nice and wide open eyes right here. Now I want you to contrast this picture with if I change the roll-off factor down to the 0.5. So remember, this has the advantage of tightening up our frequency domain at the expense of loosening up our time domain. So maybe if you can, before I hit play, picture what'll happen to the eye diagram. Cool. So if your mental model said it should get worse, congratulations, it got worse. The eyes are more closed, and the idea is that the taller this opening is, the more noise immunity you have. That is, for any given noise power, the less likely it is that this sampling instant is going to get bounced down here. And then the wider horizontal opening is the immunity to timing errors or timing jitter. So the fatter this crossover becomes, the harder it is to determine when one bit period has ended and the next begins. And so we can actually go a bit further down to, let's try 0.01. This would be, my bandwidth is super precious and I can't go outside of it, but I'm going to pay for it because all hell has broken loose in the time domain. I mean, we get, like, if you can ensure perfect timing, then this actually has pretty good noise immunity. This maximum level is about as high as it was for a Unity roll-off. But ensuring that timing has become way more difficult because of all this, the tininess of the black open space and the largeness of the ambiguity here. In fact, I think that we just, we may have broken the Simulink measurement device over here. This is a setting of like how you can measure what's going on and quantifying how good or bad your eye diagram is. I think if we set this back to somewhere in the middle of the road, Let's do 0.8. Then we'll get, I think we'll be able to get a jitter measurement. Okay, yeah, so if you have something a little bit more reasonable, Simulink will actually spit out, and these jitters are in fractions of a bit period. So we're looking at about a 6% total jitter, which would be something that you could say, oh, look, if our timing recovery system can handle 10%, then we're good. And if it can handle 5%, then maybe we're not so good. Cool. So I like this. This is, at first, easier to set up and gives you a more realistic picture of what's going on. Any questions? So far, we have been really only talking about this line coding. And so, and again, that's if you're doing, say, wire line communication or other kind of non-RF applications, then that's fine. Like then your baseband is your passband, and there's no need to upmix to something that needs to get on and off of an antenna. But when we're starting to talk about frequency division multiplexing, we're going to need to start to talk about channel bandwidth versus baseband bandwidth. So let's go in and talk about that. Oh, he says, where's his notes? There we go. Okay, so we led off this whole discussion with a talk about Nyquist's channel capacity. And so what I'd like to do is I'd like to trace how the bandwidth evolves as we go through this transmission coding scheme. So if we've got our bits and say this is at bit rate, so at rate RB bits per second, then the idea is that you can mount 2 bits to your highest frequency component. So then the bandwidth of this signal is going to be RB over 2. Okay, so here we're just going to track the bandwidths as we go along. Now, once we do our line coding, and so I guess I'm assuming some kind of root raised cosine, because what I want to talk about here is how does that expand our bandwidth? Well, with the larger roll-off factor, you're going to have what we called excess bandwidth on Monday. And so if your roll-off factor is 0, then you have, congratulations, you have no spectral spreading due to pulse shaping. But if your roll-off factor is up to 1, then we could, in theory at least, end up doubling our baseband bandwidth. Okay, so now this is a new block, I think. I don't think I've used this terminology before, but this is a shorthand for serial to parallel. I guess another way you could call this is be a demux, a demultiplexer. So something that takes things that were mounted sequentially and ends up sending them out in parallel streams. And so what the idea is here is maybe we have multiple carriers. So local oscillator 1, ... local oscillator, say, n. And then this would be our upmix from baseband to passband. Where each of these oscillators are understood to be some kind of RF carrier. And so then each one of these, well, if we have n of them, so if there are ... n of these, n streams, then what we can do is we can treat as if the bit rate itself were divided by n. Can you see that? That if I have n streams coming out of this series to parallel, then each of these signal paths only see one pulse out of every n pulses that come through. So really, each of these actually see a bandwidth of 1 plus r rb over 2 over n. Okay, so this should get you interested in how FDM can help you in terms of your bandwidth. Is because each of these streams only see pulses at RB over N rate. So then that means that you would have started with RB over N to get to, as far as this mixer is concerned, it only sees RB over N original bits. Okay, and then if we're up here in the passband, then you're all familiar with the fact that we measure baseband even if it has a Fourier transform that's symmetric. This is called a baseband bandwidth, baseband bandwidth. But in the passband up here, so I guess there'll be a break here. We measure the entire pulse width. So up in the passband, we're looking at double. So here we lose the factor of 1/2. So this is 1 plus roll-off factor times our effective bit rate. Okay. And sorry, I messed up my my scheme, which was to list the bandwidths along a horizontal line here. So I intended to put that there, and I intended to put that there. To give you a sense of like just dragging your finger across the page and seeing how the bandwidths would change as we go downstream, if you will. Okay, so the takeaways, I guess, from this slide are you double anything in baseband, you're going to double it when you go up to passband, just by the nature of amplitude modulation. And the other cool thing is that by going from series to parallel, we effectively divide our bandwidth because we effectively divide our bit rate. Any questions on this? All right. There's nothing saying that you have to do this series to parallel, right? If you have only one local oscillator or if you have only one antenna, there's nothing wrong with just having this being a straight across line, and it gets mixed up and then, sorry, it gets up mixed and then sent into the channel. But this was a good way to introduce, I think, parallelization. All right, that wraps up module number 4. Let me switch over to module